let's talk about calorimetry. Calorimetry is the science of measuring heat flow, and there are multiple ways to collect data in a calorimetry investigation, but we'll describe a couple. It's based on observing the temperature change when a body or a substance absorbs or discharges heat. We use a calorimeter to do that. So this is just one example of a calorimeter type. This is what's easiest to build in a normal lab. This is two nested styrofoam cups. The outer cup acts as an insulator. The inner cup is a container that also insulates to a degree. We have a stirrer, which is the green object. Let me pick up a pointer here. This green object is a stirrer. You have a thermometer, obviously. You're trying to make a uniform solution, so you're going to stir just by up and down, aiding in the convection of the fluid, any temperature change. So you could conceivably drop a piece of metal in. You could determine the heat of fusion of ice by dropping ice in with known masses, and lots of things you can do. And this is the variety is a constant volume calorimeter. You can also do a constant pressure calorimeter called a bomb calorimeter, just a different set of conditions. But the big idea is the same, is that we're measuring a heat change between two substances. So why do we do this? Is we do this to find the heat of reaction. We do it for physical changes, for chemical changes. We do it to find specific heats of different substances, and it's kind of fun. One of the units we need is specific heat capacity, and this is an intensive property of matter that allows us to compare heat absorbed, temperature change, and mass of a known substance. And so it needs to be at least a known measured substance. It's nice if it's a pure substance, because if it's pure, even if it's a mixture, or at least know what its construct is, we can give it a specific heat capacity. So anyway, this is the unit, specific heat capacity. C sub P, because it's constant, under constant pressure. We see heat absorbed divided by mass times an increase in temperature. These are the more refined units. You can see it in joules per gram degree Celsius, sometimes joules per mole Celsius, and sometimes they'll throw the temperature unit into Kelvin. Either way, it just make sure you're following and paying attention to the units given. The specific heat of water is 4.184. Constant pressure calorimetry, we keep pressure constant, and it's used to determine heats of reaction. Now, in most of the things we'll do in our lab will be constant pressure and constant volume calorimetry. So let's move into specific units. These are some joules per mole Kelvin, or joules per gram Kelvin values, and what you're seeing is pretty marked how high water specific heat capacity is. And this is at lab conditions, 25 Celsius. And metals, as you see, have very small specific heats. These are some heats of fusion and heats of vaporization for common compounds. Heat of fusion is the energy required per mole to convert substance like ammonia from liquid to solid or solid to liquid, depending on which direction you're going. It's positive or negative. Heat of vaporization is from liquid to vapor. And the common thread you should see here is the heats of fusion versus heats of vaporization is we have a vast difference in energy required to turn something into a liquid when compared to turning into a vapor. The energy cost to turn a substance into a vapor is significantly higher than the energy cost to turn it into a liquid from a solid. So kind of understand that heat of vaporization tends to be many times greater, 4 to 10 greater than heat of fusion. The energy formula, Q equals mc delta T, we're familiar with. Energy released as heat is equal to mass as solution times specific heat capacity times the increase in temperature. If we're consistent with the increase in temperature, it allows us to do calorimetry. That way we don't have to change any signs to negative. We can just understand that we're looking for an increase in temperature, and basically that your delta T value is positive no matter what. If there was a mc delta T temperature loss, temperature gain, it doesn't matter which direction it's going. We know which thing changed temperature in which direction. So it allows us to set MCAT equal to MCAT when we're doing calorimetry, which is kind of the goal. We want to be able to compare directly energy lost and energy gained. So at some point when we do this, we should get to this. So, coffee cup calorimeter contains 150 grams of water at 24.6 Celsius. A 110 gram block of molybdenum is heated at 100 Celsius and placed into the water and the calorimeter. Contents of the calorimeter come to a temperature of 28.0 Celsius, and it's sort of implied there that that's where it becomes steady, or it stops increasing, pardon me. What is the heat capacity per gram of molybdenum? Notice how it says heat capacity per gram. This is the same thing as specific heat capacity. Okay, so there's our formula. First thing we're going to calculate is the heat absorbed by the water. And so we know water's temperature change was 3.4 Celsius. That's this value here, 24.6 to 28. And our specific heat for water and the mass gives us this value, 2132 joules. Now the concept of calorimetry tells us that this energy must have come from the molybdenum. Okay, so we can go back and calculate specific heat now of molybdenum using this principle. Q of water equals Q of molybdenum in this particular model. That energy will be equal to 110 grams of molybdenum multiplied by its specific heat times its temperature change, which was from 100 Celsius down to 28. So one more click and we have that value. There are ways to do this all in one big operation, but for now, kind of emphasizing the idea of calorimetry. Another example, 4 grams of ammonium nitrate are added to 100 mils of water in a polystyrene cup. The water in the cup is initially at a temperature of 22.5 Celsius and decreases to a temperature of 19.3 Celsius. Determine the heat of solution of ammonium nitrate in kilojoules per mole. Also assume that the heat absorbed or released by the calorimeter is negligible. This last statement just implies that if energy were to transfer to or from your calorimeter itself, we're assuming it's negligible. There are means of calculating what's called a calorimeter constant, which can tell you of a particular calorimeter type how much energy gets released per unit of temperature. But for now, we don't have to worry about that. Now we're going to work on this calculation. So we know how much salt was added. So what we're going to do is take our mass of water plus our mass of ammonium nitrate, because this is a total mass of our system, times specific heat for water. Since we put such a small mass of ammonium nitrate, we're going to assume that water has the same specific heat capacity. And then the temperature change of 3.2 degrees. This gives us a value of 1.39 kilojoules absorbed. And then we can take the mass of our ammonium to quantify how many moles we've got. And that gives us 0.0500 moles. And we have a mole value and we have an energy value. And that gives us this calculation. So there's our answer, 28 kilojoules per mole of ammonium nitrate is how much energy is going to be put into water per mole. So this is the heat of a solution for ammonium nitrate. Since the temperature went from 22.5 to 19.3, that's how much energy was absorbed in the process of turning ammonium nitrate into ions. Okay, you have an ionic compound, you're dropping it in water, it's turning into ions. There's an energy cost here. That's why this is a positive value. So I want to talk about properties of matter that make these things unique, things we can reflect on from prior years of chemistry. Extensive properties depend on the amount of substance present. Intensive does not. Heat of reaction and mass are extensive properties. Temperature, specific heat capacity, and voltage are intensive properties. Things that don't change depending on how much energy you've got. Hess's law, basically the change in enthalpy is the same whether a reaction occurs in one step or many steps. It is not dependent on the reaction pathway. This will have more meaning later. The sum of the delta H for each step equals the delta H for the total reaction. If a reaction is reversed, the sign of delta H is reversed. If coefficients in a reaction are multiplied by an integer or a fraction, the value of delta H is multiplied by that same integer or fraction. So this is a complicated diagram. We're going to kind of get into these further along through the year. But for now, we have this reaction here that occurs in 2 steps, or we can view it in 1 step. Okay, if you notice just really quickly, these 2 reactions are going together, and you should notice these cancel, and one of them's sorry, we're going to have 2 moles of oxygen, and so we'll have nitrogen, 2 moles of oxygen, making 2 moles of nitrogen dioxide. And here it is on the left is expressed as 2 reactions, okay, where this is the energy forward is delta H positive 180, and then the second reaction, negative 112, for an overall 68. And in the second representation, the same exact value is obtained. So whether we look at it this way or just this way, we have the same energy exchange. So here's a Hess's law question. Given the following reactions and their respective enthalpy changes, calculate delta H for the reaction. And here's our goal reaction on top here. So what we're going to do is manipulate our equations to turn this set of reactions, into this. So we note that we need 2 moles of carbon, 1 mole of hydrogen on the reactant side, and then 1 mole of acetylene, C2H2 on the product side. So here is our acetylene on the reactant side. This appears to be on the wrong side, but we'll come back to that. Here is hydrogen on the reactant side, and an appropriate number of moles. That looks all right. And 2 moles of carbon. Carbon's on the correct side, but it looks like we're probably going to have to multiply by 2 here. So I'm going to reverse the first reaction. I'm going to double the second reaction, and I'm going to leave this reaction the same. And so let's start ticking through what must happen here. First reaction, doubling the second. Second reaction is the third reaction as is. Third reaction is the first reaction reversed. And the sum of all those together is, and pause it if you're doing the work, 226.7 kilojoules per mole. We have another reaction. The heat of combustion of carbon to carbon dioxide is that, whereas that for combustion of carbon monoxide to CO2 is that. Calculate heat of combustion of carbon to carbon monoxide. So in this one, instead of giving you the reaction, it says you got to go from this to this. So we have to make a couple of leaps. So carbon to carbon monoxide. Okay, so we're going to have carbon plus some amount of oxygen to make carbon dioxide. And let's go ahead and balance this. Got to have that. I'm sorry, this shouldn't be carbon monoxide. So here's our first reaction: heat of combustion, carbon to carbon dioxide. Good, a lot of leaps in this question. First reaction, you got to have oxygen to make carbon dioxide, and there's our value. Combustion of carbon monoxide to carbon dioxide requires more oxygen, so we would add oxygen to that reaction, but it's reversed. And so at that point we can simplify what we've got to get the goal reaction. Standard enthalpy of formation can also be used to calculate delta H. Change in enthalpy that the standard enthalpy of formation is the change in enthalpy that accompanies the formation of 1 mole of a compound from its elements with all substances in their standard states at 25 Celsius. So standard state simply means that the elements are in the phase you would expect them to be in at lab temperature. So just to kind of reflect, the substances that are gases under lab conditions: hydrogen, nitrogen, oxygen, chlorine, and then noble gases. And that's it. Liquid, there's only 2: mercury, bromine. The rest are all solids. So anything else that appears in a question is going to be a solid, unless it tells you otherwise, because temperature is different. So standard states, what's that mean? 1 atmosphere. For a solution, it's 1 molar. For a pure substance in the condensed state, the standard state is pure liquid or solid. For an element, the standard state is the form in which the element exists under 25 Celsius and 1 atmosphere. So the values for a delta heat of formation are found in Appendix 4 of Zumdahl and on the OWL reference. But the simple association is this. Your heat of reaction is going to be the sum of the heats of formation of products minus sum of heats of formation of reactants. So here's an example. Chlorine trifluoride, ammonia making nitrogen, hydrofluoric acid and chlorine, and then there's our energy value, positive 1196. Calculate heat of formation for chlorine trifluoride. So this calculation is actually pretty straightforward. We've been given information. We need to calculate the heat of formation of one species within. Okay, so this expression, heat of formation of chlorine trifluoride, we calculated that directly in this question. And there it is. So, a couple questions. One version of the first law of thermodynamics is expressed as delta, the internal energy of a system is work plus heat, which gives a sign of convention for this relationship that is usually used in chemistry. So when heat's added to the system, bingo, we lost it. So when we look at this, let me gather up a so heat added to the system. Heat added to the system is a positive value. And same as work done on the system is a positive value. So B, C, and D fit that mold. The heat Q added to the surroundings would be a negative, an output of energy. And so that leaves us with only D as a viable option. Work done on the surroundings is the same. It's also negative. So D is the best answer for this question. Let's get another one. When 1 mole of liquid compound X is vaporized, it is observed that the flexible container containing X expands. What's the sign of Q and the sign of W? So when we have to reflect on the phase change curve for this particular question. So I'm going to get a pen for this one. If I can convince the pen to pop up. Hi, pen. Okay. So when 1 mole of liquid X, compound X is vaporized, in order to vaporize a substance, I'm going to draw a phase change curve here. Okay, where this is energy, and this is temp. Forgive my terrible axes, but you get the idea. As energy increases, temperature increases, except during the phase change, which these two plateaus are solid to liquid, liquid to gas. If we're vaporizing something, energy is increasing, okay? I mean, we're putting energy into the system, which makes Q positive. It is observed that the flexible container containing X expands. That means that work is being done on the surroundings. That is energy output. That is a negative W. So I would select B for this question. And that concludes this video. Please make sure you're taking high quality notes, or at least augmenting what you've already got. Come to class with questions. Look forward to seeing you.